The internal combustion engine is a masterpiece of engineering that converts chemical energy from fuel into mechanical motion. By igniting a fuel-air mixture, the resulting expansion drives a piston, which in turn rotates a crankshaft to power the vehicle. This process relies on the four-stroke cycle: intake, compression, power, and exhaust. This rhythmic sequence is what keeps your car moving. The engine block serves as the structural foundation of the entire system, housing the critical components that generate power. Deep within the block are the cylinders. These precision bored chambers act as the stage where fuel combustion occurs. Inside each cylinder, a piston slides vertically, forced by the rapid expansion of burning gases. At the base of the assembly, the crankshaft transforms the linear motion of these pistons into the rotational force that eventually moves your vehicle. Together, the block, cylinders, pistons, and crankshaft form the core components of the combustion engine system. During the intake stroke, the intake valve opens as the piston moves downward, creating a vacuum. This movement draws a precise mixture of air and fuel into the combustion chamber. The volume of the cylinder increases, filling with the mixture until the piston reaches the bottom. In the compression stroke, the intake and exhaust valves are both tightly sealed. The piston moves upward, compressing the fuel-air mixture into a tiny volume. This compression drastically increases the pressure and temperature of the mixture, preparing it for the upcoming ignition. The exhaust stroke is the final stage in the four-stroke cycle. The piston, having finished the power stroke, moves back up toward the top of the cylinder. As the piston rises, the exhaust valve opens. This allows the spent combustion gases to be forced out of the cylinder and into the exhaust system. The gases travel through the exhaust manifold and out through the tailpipe, cleaning the cylinder for the next intake stroke. The piston moves in a linear, vertical path driven by combustion gases. This motion is transferred to the crankshaft via the connecting rod. As the piston moves up and down, the connecting rod pushes the offset crankshaft pin, converting the reciprocating linear energy into smooth rotational torque. The internal combustion engine generates power in discrete bursts during the power stroke, causing the crankshaft to experience uneven acceleration. To manage this, a heavy flywheel is attached to the crankshaft. It acts as a reservoir for kinetic energy, helping to maintain consistent angular velocity. By absorbing excess energy during the power stroke and releasing it during the non-power strokes, the flywheel prevents the engine from stalling and keeps the rotation smooth. Without this inertia, the engine would fluctuate wildly in speed and struggle to maintain a continuous, stable output. A single-cylinder engine creates power pulses. To achieve smooth, continuous output, engines use multiple cylinders synchronized in a precise firing order. Cylinder 1 fires, contributing to the rotational energy. Cylinder 3 fires, contributing to the rotational energy. Cylinder 4 fires, contributing to the rotational energy. Cylinder 2 fires, contributing to the rotational energy. Cylinder 1 fires, contributing to the rotational energy. Cylinder 3 fires, contributing to the rotational energy. Cylinder 4 fires, contributing to the rotational energy. Cylinder 2 fires, contributing to the rotational energy. This orchestration ensures that the crankshaft receives force at different intervals, resulting in smooth power delivery and reduced vibration. Power generated by the engine arrives at the crankshaft. However, this power must be adapted before it reaches the wheels. The transmission acts as the critical bridge, controlling the ratio between engine speed and wheel speed. By adjusting gear ratios, the transmission ensures the engine operates efficiently, whether the vehicle is starting from a standstill or traveling at highway speeds. Power flows from the crankshaft through the transmission's gear sets and is transferred to the drive shaft for ultimate delivery to the wheels. To allow the engine to run while the vehicle is stationary, we need a disconnect between the engine and the transmission. This is achieved by the clutch in manual systems, or the torque converter in automatics. In a manual system, the clutch uses friction plates. When engaged, they press together to transfer power. When the pedal is pressed, they pull apart, disconnecting the engine's rotation from the gears. In an automatic system, a torque converter uses transmission fluid to transfer power. The engine spins an impeller that pushes fluid against a turbine, creating a smooth, fluid-based connection. Both systems ensure the engine can idle without stalling, providing a vital bridge between high-speed combustion and the mechanical needs of the drivetrain. The gearbox uses different-sized gear sets to change the torque output. By using a small input gear to drive a large output gear, we gain the mechanical advantage needed to start a car from a standstill. As the smaller gear spins, it forces the larger gear to move with much more force, though at a lower rotational speed. This torque multiplication is critical for overcoming inertia. Once moving, the transmission shifts gears to smaller ratios, allowing the engine to rotate slowly while maintaining higher vehicle speeds. When a car turns a corner, the outer wheel must travel a longer distance than the inner wheel. If they were locked to the same speed, one would skid or scrub against the pavement. The differential solves this by allowing the drive wheels to spin at independent speeds while still receiving power from the engine through the drive shaft. Inside, a system of gears splits the torque. As you turn, the planetary gears rotate to compensate for the difference in wheel speed, keeping the ride smooth and preventing tire damage. The connection between the drivetrain and the ground begins at the axle. Here, precision-engineered splines on the axle shaft align perfectly with the internal teeth of the wheel hub. As the axle spins, the splines lock into the hub, ensuring that every rotation of the drive shaft is transferred directly to the wheel assembly. Bolts secure the tire and wheel rim to the hub studs, locking the entire unit into a single rigid structure that rotates in perfect unison with the axle. This robust mechanical marriage allows the torque generated by the engine to be delivered effectively to the road surface, completing the path of motion. Traction is the critical link between rotational force and forward motion. When the tire meets the road, it doesn't touch at a single point, but across a deformable area known as the contact patch. As the engine applies torque, the tire attempts to spin. Friction between the rubber and the road surface resists this, creating an equal and opposite reaction that pushes the vehicle forward. This conversion relies on the coefficient of friction. Without adequate traction, the energy is wasted as heat through slipping, rather than being translated into forward momentum. The engine control unit, or ECU, serves as the brain of the modern engine, continuously monitoring complex sensor data. Inputs like airflow, crankshaft speed, and throttle position are sent to the ECU as real-time electronic signals. The ECU processes this information to optimize fuel injection and ignition timing, ensuring peak efficiency and performance. This constant adjustment maintains the ideal balance of power and economy under every driving condition. The internal combustion process generates extreme heat. Without a proper cooling system, critical engine components would expand, warp, and fail within minutes. The cooling system circulates a specialized fluid known as coolant through passages called water jackets surrounding the cylinders. As this coolant flows past the combustion chambers, it absorbs excess thermal energy, preventing the engine block from overheating. The heated coolant is then directed to a radiator, where the heat is dissipated into the outside air, completing the cycle of thermal regulation. The engine's efficiency depends on its ability to breathe. Air enters through the throttle body, regulated by the driver's input, and travels through the intake manifold into the combustion chambers. After combustion, burnt gases are forced out through the exhaust manifold. They pass through the catalytic converter, which chemically reduces harmful pollutants before releasing them into the atmosphere. By balancing this intake and exhaust flow, the engine maintains optimal power output and emissions compliance. We are now seeing the complete system in action. Fuel combusts in the engine, converting chemical energy into mechanical rotation. This rotational power travels through the transmission, where gears determine the balance of speed and torque. The drive shaft carries this motion to the differential, which splits the power to the axles. Finally, the power reaches the tires, converting the engine's internal motion into forward momentum on the road. Every component operates in perfect harmony to drive the vehicle forward. This summary explores the journey of power in a vehicle. It starts at the engine, where combustion generates rotational force. The transmission receives this force and selects the appropriate gear ratio to control speed and torque. Finally, the power is transferred through the differential and axles to the tires, creating the motion that pushes the car forward. From the initial spark in the cylinder to the rotation of the tires, this mechanical orchestration is what defines the modern automobile.